Hello, I'm Emily Branson.
I'm Elizabeth Jennings.
And I'm Colton Herrold. And we go to Abilene Christian University, and this year for our problem, we've chosen problem B, a spinning wheel. So our problem revolves around a bird on a wheel, revolving around a wheel by shifting its weight. Some assumptions we've made for our system include that the wheel rotates without friction because ball bearings produce very little friction. The system rotates without air resistance because we use masses to replicate our bird. The rotational inertia of the wheel we approximated using a thin hoop to easily calculate it. And the pistons that we used at the end of our wheel to move the wheel around can move perfectly depending on the angular position of the wheel. So our setup includes two pistons attached to the end of a wheel, one moving radially outward from the wheel and one moving tangential to the wheel. And the positions of the masses change with the changing angle of the wheel. So as the wheel rotates, the masses extend on the right side of the wheel while the wheel is moving, the masses are moving downward, and retract on the left side of the wheel while the masses are moving upwards in order to increase the moment of inertia on the right side of the wheel and decrease the moment of inertia on the left side of the wheel.
So these assumptions that my friend Colton has described led us to these equations of motion. This top equation here, h of phi, describes the radial position of that mass which is able to move radially outward with respect to the angle phi of the wheel. And we were able to describe that using a sinusoidal equation as shown below. H of phi is equal to a capital H times 1 minus sine of phi plus pi plus r, where that capital H is the maximum distance our mass is able to extend radially outward, and r is the radius of our wheel. Similarly, the tangential displacement of our wheel is actually described with a very similar or identical equation, simply replacing that H with an L, where that capital L is the maximum displacement tangentially our device is able to achieve, and again r is just the radius of a wheel. Combining all of that together, we receive this third equation where the term on the left, m sub w times r squared times phi double dot, is simply the rotational inertia of our wheel, mr squared, which we were able to achieve by, as Colton said, approximating our wheel as a thin hoop, and that phi double dot is simply the angular acceleration of our wheel. These three terms on the right are all three of the torques that are applied on our wheel by our three different masses. The first term is the torque that is applied by the mass which moves radially outward, so just the mass of the bird which is able to extend radially outward, mbr, times the acceleration of gravity, times the radius, plus the maximum, plus its position as it translates radially outward, times sine theta. Similarly, the second term is the torque applied by the portion of the mass which is able to move tangentially. And this third term is simply the torque which is applied by the mass of the bird which is unable to move and is affixed to the rim of the wheel. So we decided upon some parameters and some values for those parameters. First, g is simply the acceleration of gravity. That was very easy to find, just 9.81 meters per second squared. The mass of our wheel is simply the average mass of a bicycle wheel, approximately 1 kilogram. And as the total mass of a cockatoo tends to be around 0.9 kilograms, we ensured that all three portions of the mass of our cockatoo added up to that mass. We decided to say that approximately 0.5 kilograms of the cockatoo's mass must remain in place at the rim of the wheel in order to prevent the cockatoo from flying off. However, it is able to extend 0.2 kilograms of its mass up radially and another 0.2 kilograms of its mass leaning forwards. The radius of our bike wheel is 1/3 of a meter. The maximum height our cockatoo is able to extend upward is 0.02 meters, and the maximum amount it's able to lean forward is also 0.02 meters. And so plugging in all of these parameters into our equations of motion and solving numerically, we see some of these following results. So with the initial conditions of starting at the top at rest, we see the graphs shown on the right. The bird takes a little bit of time to catch up speed and start moving, but once it makes that first initial revolution, it is able to complete all successive revolutions with ease and simply continues going around the wheel, gradually speeding up as it does so. As we see on the right here, if it starts at the bottom at rest, it is not able to achieve the same motion. Though it tries and it leans forward and it is able to rock itself back and forth, it ends up being stuck in this oscillatory motion around the bottom, with its angular velocity oscillating back and forth, which is, again, what we would expect from this situation.
So a couple more initial conditions we considered were, what if the bird starts at the bottom but has a significant enough kick or initial angular velocity to send it up and around the wheel? And so we found with an angular velocity of 12.5 radians per second based on our original parameters, the bird is able to make it up to the top of the wheel, and then once it's at the top, it can carry on with its usual rotations. So then another initial condition that we considered was, because the bird's mass is not regularly placed, it has some mass sticking out forward tangentially, the bird would have to lean back a little bit to stay at rest on the top. So we found the point at which the bird can tip back on the wheel and still make it around. And so the point on the plot shows that at 18 pi over 17, the bird from the top, the bird can tip back that much and then still tip forward to make its usual revolutions. So then our model shows that the angular velocity continually increases, which we reviewed the video and saw that the bird in the video does gradually speed up until it resets itself, starting again at 0, which matches our model. And in that case, the maximum velocity is dependent on how able the bird is to respond to its position. And so this follows for our mechanism that either the bird's ability to move itself depending on where it is, or our piston's ability to move depending on where they are on the wheel, are what would limit how fast the wheel can go. So ideally, they would be able to just continually speed up indefinitely. So to conclude, our apparatus drives the wheel as the bird does, and our model shows how the bird and the wheel move. Some further improvements could be to model the bird as a continuous body rather than some discrete mass points. And that's our problem.
Thank you.